Dear friends, welcome back. In our previous lecture, we discussed about weight estimation of an electric powered propeller driven UAV, where the total takeoff weight is a summation of structural weight, propulsion weight, weight of the propulsion system, weight of the structural system, and of course there is a payload which is guided by the mission requirements, and then what you have is fuel weight or battery weight. So we can express this equation in terms of weight ratio, right? And propulsion weight ratio times the total takeoff weight, and payload is a given input, and W battery need to be estimated as per the requirement, right? Now in our previous lecture we solved an example where we figured out what should be the weight of the battery depending upon the energy or the energy requirement of the system, right? Energy required by specific energy density is the total weight of the battery required with some efficiency factors. You can, so by using this we estimated the total weight of the battery, right? While doing that, we assume there is a known takeoff weight. Takeoff weight is known, but say if you are starting a new design of a new UAV where you have only a mission requirement, set of mission requirements, but you don't know what is the overall takeoff weight, how to start or how to solve that problem, right? So the approach that we are going to adapt here is a iterative approach, right? So how we are doing this? Now, based upon the payload, weight of the payload or the mission requirement, you can consider a nearby UAV, a UAV which can perform the similar, may not be the same, but close to that, right? You can consider the data of those UAVs, right? So from those UAVs, step 1, consider W takeoff, right? To start with, W structural by W takeoff and W propulsion by W takeoff, right? So consider these three parameters from the historical database. So typical value for a fixed wing UAV, the ratio of structural weight to takeoff weight ratio for a fixed wing UAV will range from less than or equal to say 0.4 or 0.35, 0.15 to 0.4, right? And typical values of propulsion to takeoff, 0.2 is a maximum case where we are considering and will lie 0.05, 5% of the overall takeoff weight, right? And now you also consider the input of this overall takeoff weight. So by doing so, what we are doing, what we have this is, this equation that is presented here will talk about the UAV which is closer to the mission requirements, current mission requirements. Now how we are in fact this represents exactly the same weight estimation of the previous UAV, right? Now what we have to do is bring this equation to the current UAV, current mission. How we are doing this? So initially by estimating, you know the payload and the mission requirement, right? So that means this is known here. Let us say if this is known, then using these parameters you get to know what is the battery weight, right? Okay, by doing so you can estimate initial idea you can get an initial idea of this battery weight, where W payload is an input. Input from mission requirements, right? So using this equation, we have numbered it as W weight estimation 2 or 3. What is the number? Say this is WA2, so you will get the initial idea of weight of the battery using WE2, right? But we are not going to use that now. That parameter is not of use right now. So with this takeoff weight, let us say, and you are going to perform a mission that is of the current requirement with the new mission requirements. So that means so this weight of the battery that you are estimating the weight of the battery from here, right, which is from the previous UAV data. Then ultimately you will end up getting the weight of the battery which for the previous UAV, right? But now we want to figure out what should be the weight of the battery for this particular mission requirement, right? So how to do that? The same procedure, like we need to know what is the energy required for this particular mission or the new mission, and you should know what is the corresponding specific energy density of the battery. So how we proceed? So the major consumption of this energy is during the cruise that we have witnessed. So let us start with the cruise, right? So what is energy required? It's a power required into delta T, time of flight during cruise, right? So how do you get the power required? So for cruise, you have L is equals to W, T is equals to D, right? So what is power required? Is thrust required into velocity. What is thrust required? It is W by L by D into velocity, right? So substitute this in the above equation, energy required equation. So substitute this power required in the energy required equation to get weight of the system or the total takeoff weight multiplied by V infinity into time of flight divided by L by D. So V infinity will be a part of the mission requirements. So how to get this? So V infinity is input from mission requirements V infinity can be directly derived or directly or indirectly can be derived from the mission requirements, right? The velocity of cruise flight. Now you need to know, so you have the previous UAV data, right? That is the takeoff weight that you have considered the nearby UAV, which can perform similar mission, right? You have WT naught, so you have V infinity, but this delta T is different, and you can assume a value of L by D. L by D is also known as aerodynamic efficiency, right? So assume. Right. So typical values of L by D will be 8 to 12, 8 to 14 for a normal, UAV which is with an aspect ratio of 10 around, right? For a glider kind of UAVs, L by D ranges from 15 to 20. Anything between that. So these values can be considered as an input from historical database. Yes. So the only assumption that you have to do here is what is the corresponding L by D, right? And from once you know the L by D, you have WTO and V infinity and the time of flight. So you can figure out what is the corresponding energy required. Once you know that, once you have this energy required, you can estimate the battery weight, which is equals to energy required by specific energy density. So you can do a market survey where you'll get to know what are the different types of batteries that are available and the corresponding specific energy density. So you can select one of those and use that number here to figure out the corresponding battery weight for this particular mission, right? So what are we doing? We have W takeoff from the previous aircraft, and whatever the battery that you have estimated is for this particular mission, because this delta T, V infinity and L by D are this particular mission required, right? Now once you have this number, you go back to step 1 again, right, where you can estimate this W battery using this equation, right? Now update this W battery value with the step 2, result from this step 2, right? Try to update this battery value. So once you have updated this, you keep this, you keep these two parameters constant during this initial iterative process, right? For the time being, assume these two terms as constant, as a constant. So during the first iterations, once you assume the value of ST by WTO and PR by WTO, right, multiply by initial weight of the UAV, right, which is again from the historical database. Now fix these two values, you don't iterate these two values. The only thing is we are trying to change the battery. While considering them as a constant, what we are assuming is the structural weight and the propulsion weight are good enough to satisfy the UAV with the current requirement, right? So that's the initial iteration to start with. So what we are trying to do, we are adapting this equation to the new UAV by updating the battery weight, right? Now you have updated the battery weight, the overall takeoff weight again changes, right? Now for the new takeoff weight, again the energy requirement changes. Why? Because you have takeoff weight as a energy requirement as a function of takeoff weight. Now again estimate what is the battery weight here, right? Now update this equation again with this battery weight, right? So you need to update this until this cost function becomes very less. You can define this error, right? So W takeoff I plus 1 minus W takeoff I should be less than or equal to some error. You can define this limit of this error, right? So if you keep iterating this, finally you will end up having the battery weight that should satisfy this particular mission requirements. Once you arrive at this number, right, so or this cost function satisfies, now what you do is update the propulsion weight. How can we update? We already looked at how to figure out an engine based upon the power requirement of the system. We are actually calculating the power requirement here, right? Now you see what is the maximum power requirement based upon this mission requirements and try to select a particular engine, right? Now once you have the engine, you will have a accurate weight here, almost accurate weight. Now update this particular parameter, right? And moreover, we know that a power plant can deliver a range of power. It is not that it is designed only for a particular power requirement. It can deliver a range of power, right? So that means a selected power plant can take care of the change in the battery weight again, because now you have an updated weight here. What happens is again the overall weight of takeoff weight changes because of it. So now you have to repeat this process again to update the corresponding battery weight. See, we are slowly adapting the previous equation for the previous UAV to the current UAV to satisfy the mission requirements, right? Now the power plant is updated, which is selected by means of based upon the power requirement of the system as per the new mission requirements, right? Now you have updated this parameter, right? Again do the iteration, fix this value, and this is again considered as a constant, right? Or the new takeoff weight after this iteration, right? You can consider that as an input here. You can update this, assuming the same structural weight ratio, and you have the new takeoff weight, update this parameter, and make it as a constant for the second round of iterations, right? So again you end up having a different battery weight, right? The final battery weight due to the updated propulsion system weight as well as the updated structural weight, right, is arrived by means of minimizing this error. So we'll write the steps for this. So once you have that, then you can consider this equation, right, for this weight estimation for this current UAV. Now once you have this battery weight as an output of the second round of iteration, right, so this particular takeoff weight, whatever you are going to get, is an estimate for the UAV that you are going to design for the new mission requirements, right? So as we mentioned, it's an estimate, right, because most of the parameters or some of those parameters are assumed. So it's an estimate which may, like, you can assume a 20% of error using this procedure. Whatever the weight that you are going to arrive at will be 20% off from the actual value, right? See, you are having an accurate weight of this propulsion system. Only thing is, once you have the structural weight ratio, or once you design the structure, you can update this parameter again and do the iteration. But to start with, or the initial weight estimation, for initial weight estimation, you can adapt this procedure, and this is, well, I mean, this is fitting with almost 50 UAVs, right? Data of 50 UAVs that we have verified, and this procedure you can adapt to figure out what is the overall takeoff weight and the corresponding battery weight, as well as which kind of what should be the propulsion system that you have to use, and for a given payload, right? And you have to, so the other way that I look at it is, so within this limit you have to design your structure. You have to optimize your structure within this particular limit, right? That is another approach which can be adapted so that the weight from each and individual components, right, will satisfy this particular equation. So what are we doing now? So step 1 is, so I am repeating this again, right, it may be a bit confusing. So what we have done, the total takeoff weight is a summation of structural weight, propulsion weight, payload and battery, right? So this equation can be expressed in the form of weight fractions, right? So the takeoff weight have a component of or is a function of structural weight ratio, propulsion weight ratio, right, for an electric propeller driven. So we are not considering a battery weight ratio here. So for an electric powered propeller driven aircraft, so this equation is, I mean, will give an estimate of the overall takeoff weight, right? Now this parameter W, or structural weight ratio fraction, is taken as an input from the historical database, as well as the propulsion weight fraction is taken as an input from the historical database. Now you have these two parameters, and to start with, we are considering the overall takeoff weight of a UAV, which is close to this particular UAV that you are going to design as per the new mission requirements. So the three inputs that you considered is W takeoff. This is at I is equal to 0, at 0th iteration, right, to start with. So W takeoff and structural weight fraction and the propulsion weight fraction, right? Now once you have this, so with the same equation, what you can find out is the battery weight with the new payload that you are going to carry, right? This is an input here, payload is an input here, right? So at I is equal to 0, you have what is the corresponding battery weight. What should be the corresponding battery weight for this new payload to carry? But the propulsion weight as well as the structural weight ratio and the overall takeoff weight are considered from the historical database, right? Say with this overall takeoff weight, with the new mission requirements, now find out what is the corresponding battery weight. How to do that? Now the power required here is W by L by D into V infinity, right? Here W takeoff is from previous UAV or the historical database, and V infinity is as per your new mission requirements, delta T is as per your new mission requirements, right, the time of flight, and L by D is an assumption that you are considering, right. So with the same L by D, with finally when you design the UAV, like when I say the design, when you select the wing area, you can achieve the same L by D, right, you can try to achieve the same L by D with that particular wing or a wing and tail combination, right. So this L by D is an assumption which you can use at a later stage as well while designing, right. So selecting this L by D is a crucial part, right. Higher the value, lesser is your energy required or greater is your time of flight. So that we already witnessed, right, during what is the maximum endurance, maximum range during that conditions. So we also witnessed that at higher L by D or CL power 1 by 2 by CD max or CL power 3 by 2 by CD max. So there are various conditions under which you can achieve maximum range, maximum endurance, right. So you have to select from one of those, right, as per your mission requirements. You can select a nearby value, may not be the exact, it's an estimate again ultimately. So once you have this energy requirement with those inputs, you can find out what is the corresponding battery based upon your available specific energy density of the batteries. Ultimately, whatever you are designing, you should be able to realize it, right? You need to make it. That means you can't have an estimate of, you need to consider a realistic value. So say SED of 0.1 is realistic, 0.2 is also realistic, but considering 0.5, when I say 0.5, it is the units are in kilowatt hour per kg. 0.5 is a futuristic thing, which is not readily available. So you need to find out, the access that you have for various energy density batteries. Right now we are having an access up to 0.25 kilowatt hour per kg. Right. If somebody finds a higher SED battery, please let me know. Okay. So from here you can figure out what is the weight of the battery. Now go back to this equation. Right. So for the same UAV, let us say, if this battery weight turns out to be the same battery weight, right, so at I is equals to 1, you will be able to converge, because nothing is going to change here. The same UAV which is available can do the new mission requirements, whatever you have considered. But the mission requirements are different, maybe the velocity may be different or the time of flight may be different, right? So generally you don't end up having the same battery weight. That means you are updating the overall takeoff weight. This is the first step where you are bringing the weight estimation of a previous UAV to your current UAV. That means you are updating this WTO by updating this W battery, and while doing this we considered these two parameters are constant, which are the value set I is equals to 0. You use don't update the WTO of this particular fraction, and don't update the WTO here as well, right? You considered whatever the value that you have at I is equals to 0, considered as an input for the entire iteration or initial iteration, entire initial round of iteration, right? So repeat this step. Now since the WTO is changed, again the overall takeoff weight is changed, and the energy requirement to perform this particular mission will change, right? So once you change this, what you have is your new battery weight, assuming the same L by D, and the mission requirement still remains same. So since the WTO is changed, slowly you are trying to bring it to your current UAV. So your energy requirement also changes. So this change in the energy requirement will reflect in the total battery weight that you have to carry. Now again update this battery weight, you will have new takeoff weight. So again repeat this process. So you have to repeat until this, you arrive at this cost function, or this cost function is satisfied, right? Now once you have that, what you have to do is, see this particular term you have updated as per your new UAV, right? And this payload, of course, from the starting, it is as per the mission requirements. That means it satisfies the requirements of the new mission. From this equation, after this initial round of iteration, you have updated the overall takeoff battery weight as per the new mission requirement. And the payload is, of course, is an input from the mission requirements. So now it's time to update the propulsion weight of the propulsion system. How to do that? We already figured out how to select a power plant based upon the maximum requirement, right? Either rate of climb or the cruise, right? So from here, see, this is just for cruise. You can also add for rate of climb. What is the energy requirement during rate of climb? That adds up the total energy requirement, right? Now again, you know what is the power requirement during various phases, what is the maximum power requirement. Now based upon that maximum power requirement, try to select a power plant. So while selecting this power plant, the only care that you need to take is, so the power, whatever the maximum power required, right, it should be delivered by the power plant at its 50 to 60% of its operating power, right? So that will help you even if the battery weight again changes, because once you select that power plant, this particular term is updated. The overall takeoff weight is again getting updated, right? That means you have to know what should be the corresponding battery weight or the fuel. In general, it's a fuel, but in case of electric powered propeller driven, it is a battery weight, right? So now, since this parameter is updated, you have to update the corresponding battery weight, right? Now consider this or update this value. At the same time, after this convergence, which is after this convergence here, like which is arrived after the first round of iteration, you update this structural weight as per the takeoff weight that is obtained after this convergence, right? So that is again updated. So what are we doing? We have an updated battery weight, we have a payload as per the new mission requirements, and your propulsion weight is also updated as per your new mission requirements, and now you are actually updating the structural weight. But in this case, you are still considering the structural weight ratio, right? You still have this ratio as an input from the historical database. Since the weights are updated here, again the total overall takeoff weight changes. That means the battery weight need to be again estimated, right? Now do the second round of iteration, right? So second round of iteration, again estimate with the increased takeoff weight, estimate the corresponding energy requirement and the weight of the battery, and update the takeoff weight and arrive at this, iterate this process until this cost function is satisfied. So this is the second round of iterative process. Okay. So but see, the advantage, again you can ask, like, see, the power requirement again changes since the takeoff weight changes here even after the second iteration. But we are considering the power plant, whatever we are selecting here, by doing with this algorithm, we are selecting a power plant that can operate at the 50% of the maximum requirement, right? So this will take care of, say, 20 to 30% of increase in the power requirement. Similarly, the structure, whatever you are going to design, it will have a factor of safety, and it can, so the aircraft or the UAV that is designed to carry 3 kgs will not change for 2.5 kg. The structure may not change significantly for 2.5 kgs, right? So that factor of safety, you need to consider a higher factor of safety so that this iterative process can be minimized, or the rounds of iteration can be minimized. So maybe in the first round it may take 10 iterations, in the second round it may take another 10 to 15 iterations to converge, right? So after 2 iterations, it's like more or less a good estimate of initial takeoff weight for your particular UAV, right? This is a whole iterative process. You can numerically solve this by using MATLAB or any of the programming language, right? So I have something for you right now. It's a symmetric wing. Of course, I can see a bit of, what do you call, asymmetry, but that's fine. Okay, it's a symmetric wing made out of symmetric aerofoil, right? It's of 1 meter span, and there is a boom that is helping me to hold this particular wing, right? So this boom is passed through this 2 balsa wood blocks, right, attached to this wing. Now let us see what is the weight of this system. How can I do? Put it on a weighing scale. So is it 0 initially? Yes. And it is approximately 148 grams, right? Okay, that's good. How much weight this wing can carry? Or with this wing, what can be the weight? What is the maximum limit of the weight with which I can fly? I can still fly, right? We'll address that by wing sizing. Now, let us write down the steps, final steps, how to find out the weight of the UAV, right? Or weight of the battery, or the initial weight estimate of a UAV as per the mission requirements. Now, what you have done, we have step 1 and step 2, right? So step 2 helps you to figure out what is the energy required, which is W by W takeoff into V infinity into delta T by L by D, right? And corresponding battery weight can be figured out by energy required by specific energy density of the battery. Okay. So start. So in this algorithm, what you have is to start with W takeoff is W ST by W takeoff into W takeoff plus W propulsion by W takeoff into right. You start with this equation and consider this as constants. Which is effectively constant, and this one also constant, right? So yeah, from the historical data, these two are constants. So you have W takeoff weight. Now to start the iteration at I is equals to 0, I is equals to 0, you estimate what is the corresponding battery weight with this takeoff weight, right? With given V infinity L by D from V infinity delta T, right? And WTO and L by D from historical database. These are from mission requirements. These are from historical database. So SED from the market availability. Do a market survey and get to know which kind of specific energy density batteries that you can have. Right. So you'll get to know what is the overall takeoff or the battery weight here. Now once you have the battery weight, you update the takeoff weight. Right. So with the new takeoff weight at I is equals to 1, you have updated takeoff weight at I is equals to 1 with the corresponding battery weight. Right. Battery weight at I is equals to 1. So this updated takeoff weight you obtained from the initial battery weight that you have estimated at I is equals to 0. Now with this takeoff weight, again find out what is the battery weight at I. So this is obtained with I is equals to 0, right? The one that you calculated here. Now update this equation with this battery weight to get takeoff weight at I is equals to 1. That is the first iteration you are starting. It's at 0, right? It's an initial value. And now the actual iteration starts here, right? So with this takeoff weight, which is updated as per the mission requirement, new mission requirement in the corresponding battery weight. Now try to find out the new battery weight at I is equals to 1, right? So after this first iteration, you have battery weight at the end of first iteration, right? Now find out the overall takeoff weight at iteration 2. Right. Say I is equals to 2 right now. Now you are entering second iteration. Find out what is the takeoff weight at I is equals to 2. This is the starting of I is equals to 2, which is obtained from battery weight at the end, at the end of first iteration. So this is updated with the battery weight that is obtained. So before proceeding further, you need to see whether takeoff weight at I plus 1 or I is equals to 2 minus I is equals to 1, I is less than. Ideally it should be, if it is equals to 0, the difference between them is equals to 0, then it's good. Otherwise, see, give certain limit, 10 power minus 6, which is 0.000, right? So if that is the case, then you can have, you can consider the new takeoff weight as a updated weight and the corresponding battery weight for the new UAV, right? Okay, this is round 1. Round 1. Round 1, you do these iterations. Right. So after round 1, once you achieve this, what you do is update W takeoff equation. That means, what are we updating here? Already we are updating the battery in each and every iteration. What are we updating here? The propulsion weight ratio, or the total weight of the propulsion system. This you can figure it out by calculating the power requirement during various phases, or the maximum power requirement, and select a power plant that delivers this required maximum power requirement at 50% of its operating power, right? After all efficiencies, after considering all efficiencies, so this should deliver the required maximum power at around 40 to 60% of its operating power, right? Or the maximum power, maximum operating power, right? Now you have WTO, updated WTO, right? Why? Because W takeoff is equals to, say, W structure, which is again a ratio. This is updated from here. At the end of this iterative first round of iteration process, like the iteration, there can be n number of iterations in this first round. By the end of this first round, you will get a particular takeoff weight. Update that particular takeoff weight here with the same structural ratio. That means this particular structural weight is also updated as per your new mission requirements. And you have the propulsion weight here. So propulsion weight can be readily considered as an input. Why? Because you are actually selecting a power plant, and the details of the weight of that power plant are available from the manufacturer, right? So this is, again, it is not an estimate anymore here, right? It is an accurate value. Payload is an accurate value that you will consider, plus battery. But this battery is what the weight of the battery that you obtain after the by the end of first round of iterations. But since you have updated the propulsion weight as well as structural weight, these two parameters, so this has to change again because the overall takeoff weight is changing. Now repeat iterations. Iterations as performed. So this is round 2. This is round 2 of weight estimate, right? As performed in round 1 of weight estimation, right? So again, you need to update until you get this cost function. This cost function is satisfied. So you'll get the final takeoff weight, the propulsion weight, payload, as well as the battery weight by the end of this iteration process. Now once you have this weight, right, and you know what is the velocity of flight, as per the mission requirements, you know what is the altitude of your cruise, right, you need to figure out what should be the area of the wing or the reference area which I need to consider, right. So that is wing sizing. So how you are doing this wing sizing? So what are the wing parameters in the first place? We discussed about some of the planform parameters, right? So you can have a rectangular wing, you can have a tapered wing, tapered about midpoint, or okay, tapered about midpoints of the chord, right? Tapered about trailing edge. Right. Say, or an elliptic wing. Or an elliptic wing. So there can be many planforms, right? So what are the major parameters that we need to consider here while sizing the wing, and why we need to do that, and how they are going to help us? Right? These are the questions that need to be addressed. So aspect ratio, which is b square by s, we already discussed about it, various aspect ratio wings, and the taper ratio, ct by cr. So ct by cr also help you for the structural design, right? Why? Because as the taper changes, the lift distribution changes. The whole idea of the taper is to make it elliptic as far as possible, the lift distribution to be elliptic as far as possible, right? And also as the taper changes, the amount of lift generated by each aerofoil changes there. That means near the chord, near the root, you will have a bigger chord, root chord, and as you progress towards the tip, you have a lesser chord, right? So that means the lift generated near the root is higher compared to that of the lift generated at the tip, which means the bending moment about the root or the fuselage reference line is more, is more or less, let us say if you use a rectangular wing, the bending moment that is produced because of the lift at the tip is more compared to when you use a tapered wing. Right? Understand? So that optimization can also be carried out by varying this lambda. Right? So by varying the taper, you also can you will also modify the lift distribution. Of course, you will modify the lift distribution along the span. At the same time, it also helps you for the structural design, right? And twist. If the root chord and the tip chord are of same aerofoil, and say if the root chord is not aligned with the tip chord, then you will have a twist, right? Geometric twist. And you can also have a aerodynamic twist, where the tip chord aerofoil, the chords of the tip and the root are in the same line or in the same plane, or say parallel plane to the ground, but the aerodynamic the aerofoils are different. That means the lifting characteristics are different. So by doing that, you can still vary the bending moment as well as the lift distribution, right? So there are two types of, although both of them have advantages as well as disadvantages, right? Geometric twist is really difficult to manufacture from a manufacturing point of view, right? Aerodynamic twist, again, in both the twist, the issue is either geometric or aerodynamic. The issue is you will start losing the lift, right? When you change the angle of attack of the root and the tip, that means as you progress along the span, you are trying to vary the angle of attack. The twist varies the angle of attack, which effectively varies the lift, CL, or the lift coefficient at that particular, or the overall lift coefficient will be reduced compared to that of a untwisted wing, right? But the advantage is we want the root to stall first, not the tip. That means you will give a negative twist. You will reduce the angle of attack as you progress along the span or as you progress towards the tip, right? That why? Because we will have control surfaces, ailerons, which are responsible for the roll control at the tips. So we will excite the ailerons to recover from the stall. So we don't want the tips to stall. That's the reason why you can. That's another reason why you need to have, twist along the wing. Now during this initial wing sizing, what we do is we assume aspect ratio and lambda are lambda as inputs from the historical database, right? Now what this wing has to do in the first place? It has to generate lift to overcome the weight and make the flight possible, right? So the whole idea is W is equals to L, or the overall takeoff is a design lift. So you have to design your wing to generate this lift, right? So this is half rho V infinity square S into CL design is equals to W takeoff, right? So this is, so CL design is equals to twice the wing loading divided by density at that particular altitude into velocity of flight. So remember this equation, right? We'll discuss about how to arrive at this particular area for a given weight of the UAV and the altitude of flight as well as the velocity of flight, right? So we'll figure out what should be the corresponding CL design and the corresponding wing area, right? Okay, we'll discuss this in the next lecture.